we don't see shadows on the face.
You're all set.
Okay, great. Okay. Well, thank you everybody for coming, and we welcome, I guess, Chapel Hill and NCAT as well. And this is the first of the Distinguished Seminar Series that's going to be officially launched actually next fall, but we do have 2 lectures for the rest of the semester. One today, of course, this is the first one, and the other one on the 5th of May. At any rate, it's a pleasure to have Dr. Muralidhar Rangaswamy from the Air Force Research Labs at Hanscom Air Force Base in Massachusetts. And Dr. Rangaswamy did his BS at University of Bangalore in India and got his MS and PhD from Syracuse. And he got a distinguished, I guess, postdoctoral fellowship from the Research Council, the U.S. Research Council, and worked at the Air Force Research Labs and has been there since, doing a lot of work in radar, and which he'll be talking about today, of course. And he's also co-organizer of many conferences, one of which is actually coming up very soon in June or July. July on space-time sensor array and multi-channel, processing. And today he'll be talking about space-time adaptive processing for heterogeneous clutter scenarios. And thank you for coming, and it's a pleasure to have you.
Thank you, Hamid, for inviting me over. Again, it's a pleasure to get out of the office. Honored to be the first distinguished speaker at the seminar series. So thank you all for coming to my talk. My work over the years has focused on the problem of radar target detection. I realize that not everybody in the audience may have a background, so I'll try to keep the material as simple as possible, but at least give you a flavor of some of the mathematics involved, because you might find similar paradigms in your own fields of work. This is actually, so to speak, a very condensed version of a number of topics that I've addressed over the years. I'll try to give you a snapshot of 2 important problems that are currently plaguing radar systems from an adaptive signal processing standpoint. My work over the years has resulted in sort of a short course, which could go for between 3 and 3.5 hours. And what I will be presenting today is going to be a subset of the lecture notes, if you may. Having said that, my presentation outline, this is actually a more detailed outline for my course, but I'll be focusing on just these 2 bullets: the contamination or outlier contamination of training data and the outlier removal for space-time adaptive processing, and what are the resultant issues. Now, to just give you some background of what's going on, I've got to skip a number of slides here to get there. Oops. All right. Here is a typical airborne radar scenario. From an airborne platform, the radar looking down on the ground. The radar receiver front end consists of an array of antenna elements which receives radiation from one or more sources. And these could be in the form of buildings, trees, land, and one or more targets of interest. The radiations from these sources are in the form of electromagnetic plane waves propagating in free space. And these plane waves induce a voltage at each element of the array, which constitutes the measured data. And to introduce the temporal aspect of the problem, you could sample this phenomenon or get the sample data from the array at several time instants corresponding to snapshots. So thus you have the temporal dimensionality coming on account of the snapshots and the spatial dimensionality coming about on account of the array. Now, given the spatio-temporal data that you have, 3 important problems arise. One would like to know whether there's a target present or not, which motivates the detection problem. B, if there's a target present, I'd like to know what its complex amplitude is, because the complex amplitude embeds important cross-section information pertaining to a target, and that's valuable in calculating the signal-to-noise ratio, which is an important performance metric. C, if one is operating in a hostile environment where there are one or more jammers trying to disrupt operation, one needs to know the direction in which these jammers are arriving with respect to the area manifold so that one can place nulls or radiate zero energy the direction of these interfering signals. A common unknown in all of these three problems is the spectral characteristics underlying the interference at hand. See, typically what happens is the radar illuminates a particular region, which you could divvy up based on the airborne platform into a number of contiguous cells, resolution cells, which correspond to a particular angle and Doppler, which arises naturally on account of the geometry of the problem. I'll spare you some of the details there. But you point at one cell and ask the question, is there a target present there or not? And you don't know the spectral characteristics underlying the interference in that cell. Interference denotes returns from extraneous objects such as building, trees, water, land, and one or more jammers, and that's like clutter, plus this background white noise. So all of these effects are lumped together, so to speak, in quote-unquote interference. And the challenge is to separate out the target returns against a background of all of these spurious returns. So the key is in order to be able to accomplish this in a statistical framework, one could go ahead. One has to know the dependent structure or the spectral properties underlying the interference. And since they're unknown in practice, one has to estimate these spectral dependencies using training data. So the way in which we collect training data is illuminate a given patch, focus on this particular cell, and ask the question, is there a target present? You allow for guard cells on either side of this test cell and go out symmetrically in range to collect independent, identically distributed data, which would be representative of the interference in the cell under test. Now, just by way of introducing you to some of the system and environmental effects that could prevail, one commonly encounters a variation of the clutter spectral properties or the interference spectral properties as a function of range. And then there could be discrete, like dominant reflectors such as tall buildings, tall trees, something like that, which contribute to the overall return. Heterogeneity is caused on account of the land-water interfaces corresponding to the surveilled region. And then there could be an internal clutter motion caused due to the platform effect, all of which impose the condition that you have only a finite amount of data available to train and learn these spectral properties. And then there is the issue of flight formations, which gives rise to dense target environments, where in the training data you have outliers that resemble a target of interest. Now, there's been a lot of work devoted to the problem of learning these spectral characteristics, applying these in an adaptive manner, looking at the performance of various radar receiver structures, and benchmarking their performance with regard to an optimal. And the frequently used metric is the number of training data snapshots, or how much data do you need to learn these spectral characteristics in order to attain performance within 3 dB of the optimal. And the seminal work of Reed, Mallet, and Brennan showed that with twice the system dimensionality, twice the dimensionality of the problem, if you have that many training data snapshots, you would get to the 3 dB performance under some idealized assumptions, quote unquote. So the processing chain consists of looking for a target in a specific cell, and then allowing for guard cells on either side of this test cell, moving over symmetrically in range to collect the training data, using the training data to form an estimate of the spectral characteristics or the dependent structure, the covariance matrix underlying the clutter. Under Gaussian statistics, the maximum likelihood estimate given by the averaged outer products of the individual training data realizations is the maximum likelihood estimate, which has two important properties, namely it's unbiased and B, it's efficient in that it attains the Kramerov lower bound with equality in the limit of large data records. So now this quantity is then inverted and applied to a steering sequence or a pointing direction, where you focus on one given cell and say, hey, is there a target present here or not? To form a test statistic when applied to the primary test cell data. And now this quantity is then compared to a threshold which is set according to a prescribed false alarm rate. And the false alarm rate is merely the probability of incorrectly declaring a target is present when there is none. Okay? And typically in radar systems, this is on the order of 10 to the minus 6 to 10 to the minus 8. Having made those comments, like I must say that these secondary reference cells that are used to infer the spectral characteristics are assumed to be independent, identically distributed, and representative, target-free, no contamination. Now, on the other hand, if I have like outlier contamination of this training data, the estimates tend to become poor. And these result in target cancellation as well. So that degrades the signal to noise ratio and perforce the ability to see a target. Because under the Gaussian assumption of Gaussian statistics for the interference, the probability of detection is a monotonic function of the signal to noise ratio for a fixed false alarm probability. Alan Nyman Pearson.
In your learning, your secondary data cells are target free.
Assumed to be target free. Now I'll then address the problem.
In the learning, you know that they're target free or not?
But yes, essentially in this training sequence, yes, the goal is to pick data that is target free. But in practice, that may not be ensured. So I'm going to discuss a couple of approaches which can be used to weed out those target-like signals in the outliers and thus give you cleaned up training data. So let me just skip a few more steps here. Okay. So now, when I go ahead, the outlier contamination of training data, which is what I refer to as non-homogeneity or heterogeneity of the training data, frequently occurs in a number of contexts for STAP applications, space-time adaptive processing. The training data non-homogeneity has an extremely deleterious impact on the STAP algorithm performance. Two important effects that come about are the undernulled clutter, which leaves you with a large residue and thereby degrades the false alarm rate performance. And B, because of the undernull clutter, you're seeing a lot of the clutter residue. There's it degrades the signal to noise ratio and perforce the detection performance. Now, this problem has received attention in recent times. There was Ray Nitzberg in 1990 who noted that the performance of the sample matrix inverter degrades significantly in the presence of these outliers. Rabideau and Steinhardt in 1999 came up with a par-selected training rule. In other words, they looked at training data, and those training data sets which shared the same par levels were used as representative training data sets to learn the spectral characteristics. And I myself, along with some of my colleagues, looked at this problem too in early 2000. The first question we need to ask ourselves is, what do we mean by non-homogeneity or heterogeneity of the training data? Let's say I get two random vectors, xt and x sub s. Now if I look at this condition, RT inverse R sub s, where RT is the covariance matrix on x sub t and RS is the covariance matrix on x sub s, if this condition RT inverse RS is not equal to the identity matrix, then I declare xt and x sub s to be non-homogeneous, okay, or heterogeneous. They do not share the same covariance structure, same spectral content, or same spectral structure. Now you might ask the question, hey, if this is all the problem at hand, why not just go after an eigenanalysis of this quantity, RT inverse RS? And then if the eigenvalues are close to unity, case closed, problem solved. Okay. The reason for doing that is, you may recall from the block diagram where I discussed the processing of the data, you have only one cell from which you can get the R sub s, okay, the illuminated signal, the illuminated patch for signal presence. And thus, if I take an outer product of that vector with itself, it's going to result in a singular matrix, okay, and therefore, the eigenanalysis of RT inverse R sub s cannot be undertaken, okay. So now, it turns out that because I don't have sufficient realizations for forming R sub s, I need to look for an alternative what's going on here. Okay, so I need to look at an alternative method for cleaning up the training data of outliers. For this purpose, I consider a simple quadratic form, which is known as the generalized inner product in the statistical literature. In my opinion, it shouldn't be called a generalized inner product. This is simply like a quadratic form arising from the inverse of the estimated covariance matrix. Okay? So now, but just in keeping with the notation of the inventors, I went ahead and adopted the same notation. You could estimate the covariance matrix from training data that's independent of this test data vector. And you want to be able to form this averaged outer products, apply it to form a quadratic form of this manner. Now it turns out that this quadratic form is very important. Like if you have like large amounts of training data, then you get perfect estimates of the covariance matrix, and the quadratic form simply has a chi-square distribution with n complex degrees of freedom, where n is the dimensionality of the vector x. And this is assuming that the vector x and the training data are representative or share the same covariance properties. Now, previous work in this field compared an empirical quadratic form, okay, based on the estimated covariance matrix, to a theoretical mean which is obtained corresponding to the fully known covariance matrix. Now, when you're estimating the covariance matrix, you have finite amounts of data, but then like the theoretical mean that was used in previous work assumed that you had infinite amounts of training data. As a result, you found that there were large deviations which came about on account of using this metric. And these large deviations were ascribed to the heterogeneity of the data somewhat incorrectly. Now, this approach would have been useful if you had large amounts of training data, but unfortunately in practice we do not, and therefore one has to modify the technique somewhat. In practice, we have only finite amounts of training data, limited training data, and hence the empirically formed GIP exhibits considerable variability. And now the approaches, therefore, which rely upon k tending to infinity or infinite number of samples for estimating the covariance matrix, would give you misleading information. In other words, you're incorrectly ascribing a finite sample support effect to a heterogeneity effect. Okay? How do we go about fixing the problem? It turns out that when you use finite amounts of data in forming that covariance matrix, you could go ahead and get a unique statistical representation for this generalized inner product. It's simply a constant of times a ratio of two independent chi-square distributed random variables. Okay. Now, this chi-square distributed random variable comes about on account of the perfectly known covariance matrix, and this latter chi-square distributed random variable comes about on account of a loss factor, okay, introduced by the finite sample support condition. Okay. Now, given these two, and here are the distributional properties, note that it's only strictly a function of the system parameters, where m is the spatiotemporal product, number of antenna array elements times the number of pulses processed in the coherent processing interval, and k is the number of training data snapshots used to estimate the covariance matrix. And it doesn't depend on any other nuisance parameters. Now, using this, what one can do is readily calculated statistics. Okay, the mean is given by this formula, and as is the variance. Now, as a sanity check, what one could do is let k tend to infinity. Okay, then lo and behold, you have expected value of p as m, which is simply the mean of a chi-square distributed random variable with m complex degrees of freedom. Okay, and similarly, the variance too, as k tends to infinity, goes to m, which is again the variance of a chi-square distributed random variable m complex degrees of freedom. Now, we could go ahead and define a normalized GIP, which is p prime, simply p divided by k, and this quantity has a probability density function shown here. Now, to arrive at this representation, one has to go through a lot of algebraic manipulation and invoke the householder transformation. As a first step, you have to whiten the data, and then you have to invoke a householder transformation and do this repeatedly to arrive at the representation. in the interest of just a finite amount of time, I thought I will spare the audience the details on getting there. But nevertheless, this is the result. And the beta distributed random variable comes around. Or actually, this is the F distribution, excuse me. This follows the F distribution with appropriate degrees of freedom outlined here. Now, what we could do is use this to determine whether our training data sets are homogeneous or not, whether they share the same properties or not. Focus on any one region, estimate the covariance matrix from adjacent range cells, form this GIP, okay, and then we'd like to set a type 1 error, okay, which namely is the probability of incorrectly declaring that the data is non-representative when in fact it is, okay. So now I could go ahead and calculate the type 1 error in terms of the incomplete beta function shown here, okay. The incomplete beta function is defined by this equation. I then need to set a threshold for a prescribed value of this type 1 error, typically between 0.01 and 0.1. I then can solve for the threshold on the basis of this formula, okay, inverting the integral equation. Or I could, alternatively run through a series of values of lambda and then calculate a corresponding alpha and pick that value of lambda, which results in alpha equal to my 0.01, right? And then I could go ahead and set up a formal goodness of fit test. I would calculate this generalized inner product, compare it to a threshold. If it exceeds the threshold, then I would say that this particular data that I'm testing is not in conformance with the covariance matrix formed from the rest of the data, training data. Using this approach, I could then go ahead and pick those data sets that offer me the same covariance structure. Here is a plot of, yes sir.
So these tests, are you doing them on a window base?
Yes, actually it will be like on a moving window. I'll come to the implementation in just one moment.
Because your clutter may not be homogeneous.
Exactly. It's going to be in moving windows essentially. Absolutely. Good point. All right, so here is a plot of the normalized GIP PDF for several values of k. As the training data support gets large, the variability of the PDF reduces, okay, which is a well-known artifact. And here was just a simple example to illustrate that. And next, what I do is I simulate homogeneous data, okay, calculate the empirical GIP, and plot the empirical GIP CDF, the cumulative distribution function, and compare it against the theoretically predicted value. And I see good agreement between the theoretical and the empirical CDF for this set of parameters. And the same fact is borne out by a histogram plot of the theoretical PDF and the empirically generated histogram. Now I then would like to know, for different values of k, which are used in calculating the covariance matrix estimate, what should be a threshold setting for a given type 1 error, okay? So I go ahead and plot the value the alpha, okay, with k as a parameter, the type 1 error versus threshold. So this could form a lookup table, from which I can readily pull off the value of the threshold for any given alpha with k as a parameter. I then go ahead and process my data, okay? I consider data from the MCARM program, which stands for the multi-channel airborne radar measurement. This consists of radar array data from a planar array consisting of 32 pulses viewed by 11 by 11 element. The spatiotemporal product is 352. Just to keep the computations manageable, I picked the data corresponding to 4 channels and 32 pulses, which gave me a spatiotemporal product of 128. And then what I did was, actually if I go forward a little bit, I can really illustrate this pictorially. I look at a given cell, okay, I start with a large training data set, okay, pick a given cell, okay, form the covariance matrix, okay, using just twice the system dimensionality number of training data snapshots, apply this GIP procedure, okay, and then I sort through this whole procedure, look at the exceedances, okay. Now I'll be able to throw out or discard those realizations which exceed the threshold, all right. So I get like one pass of this process. Now what I do is I go ahead and like I start with k equal to say five times or 3 times the 3 times the necessary sample support, and then I down select. Okay. Now in the next pass, I'd be left with fewer training data samples and fewer. So until I get to k equal to until I get the 2m sample support. Okay. So that's essentially the method or the sliding window that I was talking about. Okay, which is used to calculate the or pick the training data snapshots. So an illustration of that technique is shown right here. I go ahead and process it in the moving or sliding window manner, and I find that at these points, okay, the training data is heterogeneous. Actually, there's some ground truth to it. There's the flight path information used to collect the data. This is clutter alone, and these I suspect correspond to the land-water boundary surfaces which are causing the heterogeneities. So essentially what happens is that here is a summary of the whole procedure, generalized in a product, estimated covariance matrix, normalized form, the PDF in terms of the F distribution and its moments, sanity check, and here is what the GIP would look when you have like target like outliers contaminating the training data. Okay, you'd see peaks all over the place. Now you could go ahead and actually sort through this whole process. Okay, essentially you form this empirical GIP. Now if you had like large amounts of training data sets, the PDF and then like the type 1 error that I discussed would lend itself to that processing. But if you have like finite amounts of data, okay, like say instead of like 5 times the sample support, you had only like say 3 times the sample support, then there would be significant variability introduced by the process. So we had to modify the technique somewhat and look at the mean of the GIP, okay, with finite sample support, and that was no problem at all because we first found L realizations of the GIP with the estimated covariance matrix obtained in a sliding window manner, and then like we looked at the theoretically calculated mean value in this fashion, took the difference between the empirical realization and the theoretically calculated mean, sort the absolute value, and retain the 2m smallest of such sorted numbers, and those realizations were then used to form the estimated covariance matrix with the prescribed sample support. Having carried that out, I go ahead and show that essentially pictorially this is what is happening. Here was the GIP before we went through the sorting process. Here is what after you go through the sorting process. So you've cleaned up all the outliers that are there in the data. Having carried out that procedure, we then looked at the performance of the adaptive match filter, which is a classical baseline STAP algorithm, which has been employed as a benchmark for many radar applications. The adaptive match filter was derived by Kai, Robbie, and Kelly. Robbie, Kelly, and Ev Reed independently. All of them arrived at the same result in different ways. Now, they were able to show that in order to get to the match filter for rank 1 signal detection upper bounds its performance, and in order to get to within 3 dB of the match filter performance, one needed twice the system dimensionality number of training data snapshots to learn that unknown covariance matrix. And so here was the plot, the blue curve here. Now, when one goes ahead and has contamination, outlier contamination of the training data, okay, namely we injected synthetic targets into the training data, and lo and behold, after carrying out a series of simulations, we found an additional 3 to 5 dB loss, okay, of the adaptive match filter. Then we went ahead and used the procedure that I just described to clean up the training data of all the outliers. And lo and behold, it nicely restores the performance to within 3 dB. So thus, this was carried out through Monte Carlo simulation. It involved a lot of work. First of all, you needed to go ahead and form the estimated covariance matrix. Then go ahead and apply the test statistic, calculate the threshold settings, okay, properly to maintain the false alarm rate. So which would involve like say 100 over PFA to get acceptable numbers, And since this is a statistical procedure, one had to repeat the experiment a number of times in order to get around the variability caused by this procedure. And then one has to go ahead and inject the target, repeat this whole procedure, and calculate the threshold exceedances to count detection probability. Having done that, you do it repeated for each SNR of interest. So as you can imagine, it's going to be intensive. Having done all of it, you produce this set of curves. This is good for analysis using simulated data. But with measured data, you have only one realization, okay, based on which you have to make an inference whether there's a target present or not. And we reason that the adaptive match filter test statistic is a good indication. In other words, if there's a target present, the statistic has to peak. Okay, that would be engineering common sense. Now we looked at the plot of the adaptive match filter test statistic with and without this sorting procedure that I just discussed when you had severe outlier contamination of training data. In other words, like we had about 60 outliers, which were at the same power level as the clutter, which contaminated the training data. And lo and behold, with the NHD performance, we were able to significantly outperform the AMF without NHD. Actually, I apologize for the curves, the two are not distinct, but the upper curve is the one which buys you back performance. Okay. Now, all of this is fine and dandy when the statistics underlying the interference are Gaussian. Okay. However, if one goes ahead and encounters in high resolution airborne radar studies, okay, where the cell sizes get very small, there are fewer and fewer scatterers present in a given cell, and thus one cannot readily invoke the central limit theorem to justify the Gaussian assumption on the clutter statistics. Okay. So now you have to go ahead and modify this procedure somewhat when you're dealing with these non-Gaussian interference/clutter backgrounds. So I carried out a similar exercise to remove the outliers, and I will be talking about the non-Gaussian problem in the next 20 minutes or so. Again, this is the classical processing block. We've got this illuminated patch here asking whether there's a target present or not. Allow for guard cells go symmetrically in range, collect representative measurements which are assumed or presumed to be independent, identically distributed, and target free. Use that to form a covariance matrix estimate, which is then applied to the primary test cell data after a certain transformation to form a test statistic and then compare to a threshold. Now, in the non-Gaussian, a lot of this seems to be repetitive, so I will just skip. Okay, and this was the multiple pass sliding window processing that I talked about. Now, what is the impact of non-Gaussian clutter statistics? The clutter returns tend to be extremely impulsive. So if one looks at a plan position indicator display, one would find that there are a lot more target-like signals showing up. And that's caused on account of the fact that the clutter has an extended tail behavior. Okay? So now this extended tail behavior is not predicted by the Gaussian assumption on the clutter. So what people in the radar community did in the past was to collect a lot of experimental data and fit two parameter families to the statistics, to account for the statistics and the large tail behavior of these scenarios. In that process, they came up with the log normal and the Weibull models for the clutter. These are largely derived on empirical studies, as I just mentioned. Whereas on the other hand, there is the K distribution, which has physical significance in that the observed statistical properties can be related to fundamentals pertaining to the electromagnetic and geometric factors of the scattering surface, giving rise to the clutter. So the K distribution fits a class of compound models or spherically invariant random process model for clutter. Now, one might ask, what is meant by spherically invariant random process? A spherically invariant random process is a random process whereby if you sample the process at arbitrary time instance, any n tuple, okay, regardless of the number of samples taken or the sampling time instance, the joint probability density function of these n samples is described by a mean vector, a covariance matrix, and a characteristic first order PDF. So let's say you have like a random vector with m components as shown here. Now when you go the non-Gaussian route, you have an arbitrarily large number of dependencies to deal with. Okay, like you could consider random variables chosen pairwise, and then like taken 3 at a time, 4 at a time, and so forth. Okay, how would we build into a PDF, a joint PDF of all of these m correlated non-Gaussian random variables, these higher order dependencies? It's obviously very difficult to do. Okay. On the other hand, what is readily available is an estimate of the first order probability density function underlying each of these components, okay, through histogram fits to experimental data. And one could also get an estimate of the covariance matrix or the spectral characteristics through power spectral density estimation techniques or through covariance autocorrelation techniques. So now, at any rate, like the problem at hand is to come up with the joint probability density function of these m correlated non-Gaussian random variables based on just the first order PDF and correlation function. And it turns out that the theory of the spherically invariant random processes helps you to precisely accomplish that. Now this vector is said to be a spherically invariant random vector if its probability density function can be expressed in this form, where Q is this quadratic form that I just introduced previously, R is known in this case, and this H2M is a one-dimensional monotonically decreasing function, okay, of the argument expressed in the form of this integral. Okay. It turns out that for this class of models, there is a representation theorem which was developed in 1973 by Kung Yao, who showed that every spherically invariant random vector is equivalent to the product of a complex Gaussian random vector times an independent non-negative random variable. And now the PDF of this non-negative random variable is denoted to be the characteristic first order PDF, because depending on the choice of f sub v of v, one could get the desired non-Gaussian structure here. Okay. Now if f sub v of v is just an impulse, okay, then what you have is a constant times a Gaussian random vector, which is the Gaussian problem. Now if v takes like a generalized chi distribution, then it turns out that the x has the multivariate k distribution. Okay. The multivariate k distribution involves a modified Bessel function of the second kind of a given order. As a result of this representation, now the covariance matrix on X is merely the covariance matrix on X is the covariance matrix of Z times the expected value of V square. So the covariance matrix on X is known to within a multiplicative constant of the covariance matrix on V. All right. So now the problem at hand is when you're dealing with measured data in practice, that covariance matrix on X is unknown and has to be estimated. Okay. How do we go about doing it? Typically, both f sub v of v, the PDF on V, as well as the covariance matrix on X are both unknown. But as a first step to addressing the problem, we relax the assumption that f sub v of v is unknown. Okay, namely, assume that f sub v of v is known. Assume that it comes from a k distribution, so it pins down f sub v of v as a generalized chi distribution. And then we want to go ahead and address the problem whether these training data sets share the same covariance structure. Okay? Now that's the non-Gaussian problem. Here, so therefore, I now consider the problem of identifying training data sets which have a specified non-Gaussian distribution and see whether these training data sets share the same covariance structure. Now since this R is unknown, I have to estimate it from independent, identically distributed, target-free training data snapshots. So the first question to ask is, what is the maximum likelihood estimate of this unknown covariance matrix? It turns out that if we go back a little bit, let's say I have this X is equal to Z times V, and I have K of these realizations in X to estimate the covariance matrix. Okay. For each x, I can write as xi is zi times vi. And now if I knew the underlying component zi and vi, or alternatively xi and vi, that would be my complete data. Okay, so I could get at the z in a straightforward manner. But what I observe is merely the x of i's, and therefore I have to go ahead and cast it in the framework of a complete incomplete data problem, which lends itself to the EM, expectation maximization algorithm, to estimate the covariance matrix. So as we know, the EM algorithm consists of two steps. At the E step, one would calculate a sufficient statistic for the missing data, or the complete data sufficient, and at the M step, one maximizes likelihood. And as Don Rubin showed in his monograph in 1987, for a class of exponential families which the K distribution belongs to, the EM algorithm has a complexity restricted only to the E step, and the M step follows as a straightforward consequence of the E step. Now, it turns out that after a lot of algebra, one can show that this R hat, the covariance matrix R hat, is given in this form, where the C sub i's are merely the expected value of the V sub I to the minus 2, conditional on that realization of X sub I, all right? So you're weighting each of these realizations by C sub I. Initially start with R hat is equal to the sample matrix. Now we would calculate a C sub I, which is readily obtained in this manner, and then calculate a new value of R hat based on this. Use the new R hat to form a new C sub I and iterate until convergence, okay? Now the transcendental nature of the estimate precludes closed form solution, and therefore one has to go through this iterative process. And clearly convergence would depend on the initial start. And I found that the sample matrix is, for these problems, is a very good start. Okay? Having accomplished this, namely coming up with an estimate of the covariance matrix to within a multiplicative constant, okay, at convergence of the Gaussian component of the spherically invariant process, I then need to address the problem. Here I have these training data vectors. All of them have the same covariance structure, but they have unknown scalings, okay, because like I have the estimates to within a constant multiple of the Gaussian component, which underlies all of these data sets. Now, it turns out that if I use the GIP that I proposed earlier, it does not offer the invariance to this unknown scaling, okay, because like I have the covariance matrix at each realization known to within a multiplicative constant, and that multiplicative constant is not known. So thus, I need to go ahead and introduce a scale invariant GIP, or a scale invariant test statistic, excuse me, not GIP. It turns out that the problem for carrying out this test is the ACE test, which stands for the adaptive coherence or cosine estimator. It's also been called the normalized adaptive match filter by other researchers. Now it turns out that this is the form of the normalized adaptive match filter. Just for ease of exposition and simplicity, I chose a very simple steering vector, but in practice one would have to use the steering sequence, which is a function of the angle and Doppler. Here I just used a simple steering vector to illustrate the concept, okay? And now this quantity by this test statistic is bounded between 0 and 1, okay? And after a little bit of algebra, one can show that here is the PDF of this test statistic, and the gamma distribution is simply the well-known Reed-Mallet-Brennan loss factor. An equivalent test statistic is namely lambda NAMF divided by 1 minus lambda, and this also has a nice PDF in closed form. Its moment is given right here. Now I could go ahead and, just as I outlined in the Gaussian case, develop two strategies, okay, one where I had like large amounts of training data and one where I had finite sample support. One method would be based on the PDF of this lambda NAMF. I could define the type 1 error, which is expressed in integral form and can be numerically evaluated. Now for a given type 1 error, I need to calculate this threshold lambda, which I can actually do through numerical inversion, okay, of this integral. And then I would form this lambda NAMF using empirical estimates of this covariance matrix, sweeping window or sliding window processing. Compare this lambda NAMF realizations to a pre-calculated threshold obtained from this equation. The second method is, to form lambda sub EQ, okay, which is lambda NAMF divided by 1 minus lambda NAMF. Its mean is known, okay, I showed you in the previous slide. So I could calculate these empirical realizations and compare it to the mean, and then take the absolute value of the deviations and retain those realizations which exhibit the smallest deviation. Okay, so same processing strategy. So now let's take a look at some examples. Okay, the results correspond to simulated data based on a physical model for the K distribution with shape parameter 0.5. The f sub v of v for the K distribution is given by this equation, and the corresponding H2M function is obtained right here. The measured data examples that I present correspond to data from the MCARM program, the details of which are presented here. Now again, let's take a look at the PDF of this quantity, lambda EQ. This corresponds to a random variable whose PDF, which is represented by an F distribution with appropriate degrees of freedom, normalized by a beta distributed loss factor. And thus one can actually numerically calculate the PDF. And here is a plot for different values of K. And clearly as K increases, one finds that the variability of this PDF is reduced. Now we then plot the probability of error versus the threshold, okay, which is namely the type 1 error as a function of the threshold. And here it has different values of K. I'm sorry, the caption is missing, but it essentially is obtained in a straightforward manner from the previous discussion. I then go ahead and generate homogeneous K distributed Clutter data, form this test statistic, set my threshold for the PE of 0.01, which translates to a number of eta 0.1454, okay, right here. And then lo and behold, as I plot it, I find that none of these data sets exceed the threshold, so which means I'm doing something right here. I then inject 2 outliers, okay, at pre-specified range bins. Now I go ahead, process the data, for each realization, use surrounding realizations, invoke the EM algorithm, estimate the covariance matrix, keep it fixed. Now form realizations of the test statistic, okay, at hand, and then go through from one range cell to another, okay, in a sequential manner. And lo and behold, at both of these range bins where I had injected the 2 outliers, I find that this technique picks it up, okay. Next, I go ahead and say, hey, this EM algorithm can be computationally intensive if I get into small values of alpha, okay, which means heavy tail scenarios. And there are numerical issues which really tend to slow down the convergence of the EM algorithm for alpha equal to 0.1. And that's due to the fact that when you invoke these modified Bessel functions of the second kind, large values of the argument and small values of the order, or vice versa, tend to result in large errors. Okay. So now I said, hey, there was work carried out by a few other investigators from Italy, which went away from the maximum likelihood estimate, but it alleviated the dependence on the H functions, which was really the bottleneck. So I said, hey, if I implement their technique and use the same procedure, am I able to pick up my 2 outliers? The same example, same data set used as in the previous example. Sure enough, I find that it does not pick up the outliers, okay, because of the because it's not the maximum likelihood estimate. And furthermore, it incorrectly declares that there's an outlier when there is none. Okay. So the message is, yes, this technique, for this technique, it's very critical to estimate the covariance matrix properly. Now, here is an example of the performance analysis with the MCARM data, the multi-channel airborne radar measurements. Again, I injected 1 outlier here because it was Clutter alone data, and set the threshold, went ahead, processed the data as I just discussed, found that it's able to pick up the outlier. Okay. So on the other hand, if I implemented the GIP, okay, which is really not suited to this problem, I find an awful lot of exceedances of the threshold, which really, tells me that I have a lot of outliers. Okay, with that, I think I should just rush through to my conclusions. Okay, I here talked about the sample support for covariance estimation in STAP problems. By the way, the two approaches, the Gaussian and the non-Gaussian statistics components that I covered were appeared in two journal articles in 2004 May and 2005 June respectively. IEEE Signal Processing Transactions 2005 and then the Digital Signal Processing Journal May 2004. And then I presented two techniques for removing these outliers and showed the impact on the adaptive algorithm performance. There's a lot of interest in this kind of work. Future directions include knowledge-aided signal processing, bringing in a priori information to improve that covariance matrix estimation. The IEEE Signal Processing magazine, January 2006, lays out very nicely future directions for radar, which has been enunciated by a number of people. I happen to be a contributing author to one of the articles. Smart sensors with feedback, knowledge-aided processing, distributed sensing, layered sensing, a lot of these other concepts which would, at the heart of it, have this adaptive processing are in order and should be examined in greater detail. Thank you very much for having me over.